All right. Hello, everyone. Thanks so much for coming to the keynote event of our 150 celebration. We have a group of amazing alumni here today to tell us about their careers and their vision of the future, and this is going to be a lot of fun. But first, as you likely know, MechE, Mechanical Engineering at MIT, goes way back to the founding of MIT in 1861. And our 150th is not the 150th anniversary of Mechanical Engineering at MIT, but it's the 150th anniversary this academic year of the first lab in the department. So in the academic year 1873-74, MIT Mechanical Engineering opened its first lab when MIT was over in Boston, where it was for about its first 55 years. And around the same time, we learned that MechE, which we know as Course 2 today, actually went from Course 1 to Course 2. So believe it or not, when MIT started, MechE was Course 1, and then 150 years ago, it swapped numbers with civil engineering. We don't entirely know why, but one reason might be that at that time, civil engineering actually had larger enrollment than mechanical engineering. So we became Course 2, and we've been Course 2 ever since. And as we looked a little bit into the history after discovering the 150 thing, we found the MIT President's Report from that same academic year, 1873-74, where the section written by Professor Channing Whitaker, who for the first few years of MIT was the only professor in mechanical engineering, where he details a big change in the curriculum and the setup of the first lab. And he goes through beautiful detail of all the pieces of equipment and the contractors that were hired to put the equipment in the lab and all the qualification and testing and safety and so on. You can find it in the library if you're interested. But that first lab was indeed the STEAM lab. And here's a picture not from that first year, but from the mechanical engineering kind of department guide that has the whole course of study that was published in 1902. And this is, of course, from MIT's original campus in Boston. Engineering Building A, as it says here, and it had steam engines and boilers and this whole host of equipment, which laid the foundation for thermal engineering in MechE, where our department, as in many areas, has played a foundational role in discovery of some really important principles, foundational heat measurements, and what leads to our amazing legacy and work in thermal sciences and energy conversion these days. When MIT moved to Cambridge, the main building cluster where we are today, the STEAM lab moved with it, or the STEAM lab was rebuilt. And this is the STEAM lab shortly after that. You may recognize this space because this is the main hallway of MechE in Building 3, where the Newman lab is today, where the Pappalardo lab is today, and where the Hatsopoulos microfluids lab is today. And you can see multi-story. The equipment was so tall, they had this beautiful high bay space, and this was used for experimentation, measurements, teaching, you name it, just like we go between research and education hand in hand today. In fact, in the same space, sometime later, the Wright brothers plane was actually on display. So that's a real picture of the Wright brothers flyer in that same space, and you can see a bunch of people taking a look at it. As MIT grew and evolved, one other important development in the history of a department was the construction of Building 35. Building 35, where we have our manufacturing research and our manufacturing teaching. And here's a picture of the machine tool laboratory, which we now call the LMP shop or the manufacturing shop. It looks quite similar in its envelope, but of course has machine tools from a much earlier age. And we also, around 50 years ago, started the course today known as 2007. It started as 270, as the brainchild of Professor Woody Flowers. And because we had the 007 finals just last night, I was reflecting on how far we've come, but also how similar the pedagogy, the principles are. And take the picture at the left, captivated audience, students watching their machines compete a challenging task, machines that they built from a kit of parts, which is the principle of designing and building something yourself and building that confidence, to the competition last night, where the machines are more complicated, there's an autonomous mode, the table is more intricate, but the basics are still there. And my point here is, as we look to the future and think about computing and robotics and bioengineering and all the amazing frontiers of the department, the principles stand the test of time. And if you want to get a sense of where we started and where we're headed, I also encourage you to stop by whenever you want. Building 5, you may know the Hart Gallery, where we have the mechanical engineering piece and then the Museum of Ship Models, maintained by the MIT Museum. Our team has done an incredible job over the past couple months redesigning that whole gallery, and we have some amazing exhibits of artifacts and historical photos and information on our courses. So it's a lot of fun to go check that out if you get a chance when you're walking around campus or after the events conclude today. But the rest of today's presentation is not about the long past, but it's about the present and the future. And to introduce our speakers, please welcome Professor Ritu Raman.
Readjust from John height here, maybe. All right, well, thank you everybody so much for being here. We're super excited to hear from all of our speakers. We have 3 wonderful speakers here today, as well as a moderator. First, we'll hear from Alice Brooks, who is a 2010 MechE alum and a partner at Khosla Ventures. Before she was at Khosla and right after graduation, she started a toy company called Roominate, which was named Time's #1 toy of 2014 and got a lot of press and excitement from Shark Tank. And then after that, she picked up a master's from Stanford, which we'll not talk about too much, an MBA from Harvard, which is okay, I guess, and is now back here today to tell us about all of the amazing things laying in the future. Next, we'll hear from Joe Petrzelka, who's a PhD alum of our department and currently the VP of Spacecraft Engineering at SpaceX. I asked Dave Hart, his PhD advisor, a couple days ago to tell me a little bit about Joe, and he said that he was so amazing that it seemed like he had the energy and the productivity of 3 students at once and was also a great mentor. So very excited to hear from Joe as well. And then we will also finally hear from Professor Asegun Henry, who is not only an alum of our department, but also currently a professor in our department who has done some really amazing energy research that he's currently commercializing as the founder and CTO of Fourth Power. And leading us all in a discussion of all of these folks will be Danny Bronstein, who is an alum of our department and also currently a senior lecturer in the head of the Papalardo Undergraduate Teaching Lab. So we have a lot of great people who have a lot of history in our department and are really shaping the future of MechE. So we're excited to hear from you all, and thank you so much.
All right, hi everybody. I'm Alice, class of 2010, course 2. And I was asked to talk a little bit about my career, where I've been, what I'm doing now. And I wanted to share that I really had no idea what I wanted to do when I graduated from MIT. I didn't have a clear career path set out, but my guiding principle was really to take opportunities where I felt like I could learn a lot. And that often meant not taking the safe bet. What I did know was at MIT, I loved building things. And I shared my yo-yo from 2008, which was my favorite class. And we made, it's Finding Nemo, he's trapped in a sushi roll, and I was responsible for the Nemo part there. So I remember spending a couple hours in the lab at the injection molding machine, trying to get the fit right so he could fit, his eyes could fit on the bed of sushi rice and mixing the pellets so the color would look right. Anyway, one of my favorite things I did at MIT. I will say, I'm still most loyal to MIT, even though that's a picture of Stanford. But when I graduated, I wanted to stay in school and keep learning. So I went out to Stanford, mostly to focus on MechE and product design. And it was great there. Honestly, it's a lot sunnier out there. I had a lot more free time than at MIT. But I also noticed something that kind of bothered me, which was I'd gotten kind of spoiled at MIT by the fact that it's a pretty even gender split in the undergrad population. But when I got to Stanford, my program was about 15% women. And I started thinking about, why was there a drop-off? What was it that got me interested and excited about engineering, where a lot of my closest friends from childhood hadn't even thought about it as an option? And I thought back, and I think I was really influenced by the things I played with when I was younger. So when I was 8 years old, I asked my dad if Santa Claus could bring me a Barbie that year, and he said, no, Santa Claus doesn't bring Barbies. And instead, I got my own saw. So I took the saw, cut up some wood, made a doll, made toys. But it was that hands-on sort of exploration, building myself, that really got me excited and gave me that hands-on confidence. So that gave me an idea, what if I made a toy that could make that a little bit more accessible? We don't expect every parent to go out and buy a saw for every child, but what could be something that they could get, that the kid could then play with and build that hands-on confidence and have a quick, easy first win that they could then play with. So that was the idea behind it, and then I really set out to try to figure out where that aha moment could be for those kids. So I went and I started talking to parents, talking to kids, watching them with their favorite toys, started prototyping some ideas. A lot of them were really bad ideas, but it was okay because I didn't spend that long on those bad ideas. Like we took a snap circuit set and hooked up a disco ball, and the kids thought it was really stupid. We had this little car set that they would hook up, and then it was, make an animal on top of it. They also sort of rolled their eyes at it. But we kept iterating. And I teamed up with a classmate in my program, Bettina, who was an EE from Caltech. And together we iterated to this idea of Roominate. And up there in the top right, that's the first iteration of the product. And it was really just made out of cardboard, popsicle sticks, these little motors that we pulled out of these hand fans. And the idea was they could build a few things. They could wire up a fan for the room that they were building. And we put it in front of about 20 kids one Saturday morning at our office. And they actually really liked it and started having fun with it. And the test there was when we took it away, some of them started crying. So we knew we had something interesting. So we kept working on the prototype. This is what Roominate turned into. It's a modular building system where you build the world that you want to play in. So modular pieces, you've got some simple circuitry that a 5-year-old could plug in. So they can put in a fan, they could put in lights, they could make their Ferris wheel go, they could light up the house. And it's all able to be done without the help of a parent. So they get those wins, they put it together and figure out themselves. So we had the prototype, we put it up on Kickstarter, raised $86,000 in a couple of weeks, and then we had to figure out actually how to make this. So we booked a 2-week trip to China. But the thing was, I knew that it couldn't be that hard to make this because the pieces were sort of on the scale of things in the yo-yo. And I run an injection molding machine, so I knew it couldn't be that hard to do. So that's us with our first mold. We were so excited when we saw it in person. Then it took a couple more weeks being there to make sure that our products got made. Then we went back to California, and that's when we received our first 2,500 units. And this was, I think, the first week of December that year. So we had to immediately after that picture start tearing those boxes open and start packing them and sending them out to our customers. We also got into retail, expanded our footprint, and all that was exciting. But the most exciting part was actually seeing the pictures we got back from our real customers. These were people we didn't know, and they were coming up with ideas that we wouldn't have thought of to do with our product. So the girl up there, I loved this one. She took the motor and she turned it into a spinning brush for her car wash. And down here we have a light up Golden Gate Bridge, things I never would have thought of. Okay, so then we got the product out there. Turns out it's not really easy to fund a toy business. You have to put a lot of money into inventory. You have to figure out how to get your working capital going. So we were trying to figure out creative ways to fund the business. So we went on Shark Tank. A little scary going into it because if anyone's watched it, they can really tear people apart. So this is, I think, where some MIT training kicked in, which is like study, be as prepared as possible. And I watched 20 episodes in 4 days, and I took notes on every question they would ask, and so we were ready for them. We got Mark Cuban to invest, and kept working on scaling the business after that. And after 4 years, we actually got acquired. And the thing that was pretty cool about that was the acquirer first heard about us by seeing this episode. So even though we were sort of scared of this opportunity, it could have gone well, it could have gone wrong, it really opened up so many more doors for us down the line. And post-acquisition, reflecting back on it, I learned a lot more in those 4 years, and this was my first real job out of grad school, than I would have if I joined a bigger company. Because I was CEO, a lot of the problems came back to me, and I just had to problem solve, figure out how to get through them. Learn by doing, figure out how to hire a team, work with a team, manage manufacturers, manage retailers, how to budget for marketing. Tried a lot of things that didn't work, tried some things that did work. But some of the lessons I pulled from MIT, which is MIT just trains you to go at a problem, do anything it takes to figure it out, be comfortable with the ambiguity around solving that problem, but also surrounding yourself with people that can help you too. So peers that have been through it, experts that have been doing this for longer, that really helped me. And I learned that at MIT, that really helped me in building the company. So after getting acquired, I worked for the acquirer for a little while. I started doing some work with some other startups. I started to get a little bored, wasn't feeling challenged, really felt like I wanted to learn more. So then I went to another school. I went and got my MBA at Harvard. I felt a little bit like a traitor going across there. But the idea was to get exposed to a lot of new ideas and people from different industries. And when I went in, my plan was maybe I'll go start another company. But for now, let me just learn as much as possible. So I signed up for a bunch of classes that I had no intention of going into professionally. I just wanted to learn about a lot of different things. And having the opportunity of going back to school after running the company, I was able to be a lot broader than I would have been at the company, really focused on one thing. And that's when another opportunity came along to join Khosla Ventures, which is a venture capital firm out in the Bay Area. And when I first started thinking about it, I wasn't that interested. It hadn't been something that was really on my radar about going into VC. But the more I thought about it, I saw that going into investing would be a really good opportunity. One, to learn from the best founders. Two, to learn from the best investors. Three, to see a lot of companies and just see the trends of what's going on. And I thought, I could do that and then maybe start another company and learn how to do it better the next time. So Khosla Ventures, our focus is on bold, early, and impactful companies. Bold being the best founders with the most exciting tech breakthroughs that others might think are impossible. Early, we'll partner as early as pre-seed or seed, something might be spinning out of a lab, all the way through growth. And impactful. This is what really drew me to it, was solving pressing problems for the planet and for human health. We look for founders that will find the problem and just push through until they solve it, no matter what. And we're actively investing. We have $3 billion in active funds that we're investing across from pre-seed all the way to growth. We invest across sectors. I spend a lot of my time in deep tech and sustainability, but we also invest across software, health, everything. The day-to-day is very different than it had been running a company. I spend a lot of time meeting with founders and really trying to dive deep quickly and figure out what the right questions are to understand about their business. So a lot of the time, it's areas that I might not have a direct professional experience in because we look at so many different things. But it's really about figuring out that problem and understanding what the key risks they're trying to draw down are and trying to dive in quickly and learn as quickly as possible. Also, I lean a lot on experts to help me as I look at different sectors. I also spend a lot of time with portfolio companies, and we call ourselves venture assistants. So it's not about telling companies what to do, it's about helping, giving advice, supporting on fundraising. We have a whole team of operating partners who have built great companies, who mentor and coach our companies. So what I thought would be fun would be to go through a few of these companies, just sort of to give sort of a breadth of the type of companies that as a MechE graduate you could go to or you could start. This, again, is only a portion of our portfolio, just on climate, because we have a good mix of things, but we also do robotics, manufacturing, AI, health, basically everything. So I'll just call it a few. So one of the companies I work with is called Leafed. They're based in New Zealand, and they're pulling this super digestible protein called rubisco from alfalfa, which is in really low concentrations, but they have really interesting breakthroughs on the chemical engineering side and on the mechanical engineering side and how they're processing it. Vertical Oceans is doing automated indoor aquaculture. We're investors in CFS, big MIT spin-out, in Fusion. We've also made another bet, which is complementary to them, called Rialto Fusion. Hertha, green steel company, the CEO, Lorraine, was a PhD in MechE at MIT, graduated a few years ago. Decoy, MIT architecture spin-out, doing sustainable building materials. Mainspring, linear power generators. Coloma, which is technology-enabled geologic hydrogen exploration. Return to Vendor, they're doing circular monomaterials platform for apparel and have some really cool material innovation there. Glideways is doing high-capacity autonomous urban mass transit. Redox blocks, industrial heat. Forterra, low CO2 cement. So it's really just a range of things. And as MechE from MIT, they need people like you. You can jump into any of these sectors. They're all hiring mechanical engineers. So I know I threw a lot of things out there, but some of the takeaways I hope you'll take from this is, one, I think it's okay not to have a linear career path. MIT gives you the skills to deal with that uncertainty and to tackle problems that you may not have direct experience in, but it gives you the framework for how you approach that. And also, I would say everything I've done since MIT has been easier than MIT, so it does get easier. And whether you go to grad school, start a company, join an early stage company, my advice would be to look for opportunities where you're maximizing the learning you're doing, because if you do that, then you'll end up working on interesting things. Thank you.
All right. Have a sound check? Good. All right, thanks so much for inviting me today. I'm really excited to be here. This is only my second time back since I graduated, shamefully. But it's really great to catch up with folks, and I'd really like, I'm looking forward to sharing some background about what I've been doing in the last 12 years. To give a little bit of a quick bio about myself, I graduated in 2012 from here under Dave Hart, but really where I started learning and tinkering with things was growing up as an Iowa farm kid. So that is at the core of who I am, and being curious about mechanical things and reverse engineering things and trying to create a different future than I was in. So I went to Iowa State. I came here for my PhD. It was an incredible experience teaching me that humans are elastic. I came from an industrial engineering program and had to come challenge myself in under a year to learn all sorts of mechanical engineering and pass the qualifiers and not get kicked out, which was a great challenge to put yourself through and prove that you can rise to a challenge. So worked through my PhD. I'm really thankful for the experience that I had, getting to do both kind of theoretical and experimental work, combining analysis with test and actually building things and creating stuff in the lab. So I thought that was really valuable. I was going to hang out and wait for a faculty position somewhere, but SpaceX really wanted to hire my wife to work on manufacturing engineering in their avionics department. And she said, well, we'll come if you can give my husband a job too. So we trucked across the country to LA in 2012. And kind of the rest is history. I've had a chance to work on kind of all of the vehicle development programs there. I characterize myself as kind of focused on vehicle development, being on the very early phases of programs, trying to take things from a binary 0 to 1. So worked on Falcon Heavy. I was incredibly fortunate to get to be the head of the Crew Dragon program from an engineering perspective for 3 years while we were returning the US to human spaceflight capability, and then I've been working on Starship for the last 3 years. I want to give a little bit of my thought process and reflection on things I found valuable there, and then speak a little bit about the Dragon and the Starship experience and show some fun videos. As I look back at what brought me to MIT, my time at MIT, my time at SpaceX, the things that I found to really be important to me or to make an impact are kind of these. First, work on the hard problems. Work on something that you feel is a really meaningful thing to solve with a group of people who are also motivated to solve it. That makes a really rewarding study or work experience. The second is to make decisions around first principles. This is just a very simple do good engineering statement. And one of the things I really appreciated about MIT when I was looking at grad schools was the mechanical engineering department here makes space for that type of just raw engineering focus within the faculty and within the work that the grad students are doing. And that carried forth into a lot of the work that I've been able to do at SpaceX. And the third is learn fast, fail fast. SpaceX, is known for not being afraid of failure and pressing into test early to learn things and push forward development programs. But I think I got a lot of that at MIT as well. Dave was always talking about lightning empiricism and go just test things in the lab and be able to combine theory and experiment together. So I think that's been able to map from both my experience here, through into a lot of SpaceX projects. So I'm going to share some SpaceX things. I'll try to loosely tie things back to these principles, but hopefully you like rocket videos. If you don't, I'm sorry, you can ignore the next few minutes. Just to give an overview of the products that I've had a chance to work on, we have a human and just a stock spacecraft there for reference. The Falcon 9 is where I spent the first 5 or 6 years of my career. I actually started not designing the rocket, but designing the machines that build the machine. So I was working on weld engineering robots. I got to design a machine that stir welds together the second stage of our Falcon vehicles. And then started working on Falcon Heavy separation mechanisms, so got to lead the team that that kicks the side boosters off of our Falcon Heavy vehicle and driving that through test flight. Got to lead the Dragon program. The Dragon is a small 8-meter tall capsule on top of Falcon. We had a cargo variant when I started at the company, and the piece that I got to work on was developing Crew Dragon, or Dragon 2, that's now flying to the space station with crew. And then the last 3 years getting to work on Starship, which is the largest rocket ever built by a factor of 2, and we'll talk a little more about the goals of that program. So this is the last slide with computer renderings that I have, and we'll just look at pictures of real things moving forward. Start by talking about my time on Dragon and just share some of the experiences there. I'm going to skip over all of the Falcon stuff. There just isn't time for it. But when I came to the Dragon program, we had Dragon 1. That it was a vehicle that goes up to the space station. It would take cargo and bring cargo back. That was operating already. And we had a contract to build Dragon 2 that was supposed to be the crew-rated version of this. And so we're able to build on a lot of the things that we knew already, but it had to be much more reliable with a much bigger focus on safety. If you think about it from the energy perspective, you're accelerating humans to 17,000 miles an hour. That's an awful lot of kinetic energy. And then you've got to slow them down to bring them home again. So those 2 phases of flight are really the ones that we had to put a lot of energy into for crew safety. The 2 projects I want to talk about, and we wound up, everything seemed to be broken at some point of this development campaign of you build a spaceship, you test it, you're having problems with everything, and you need to go do the actual engineering to create a safe system that you can make operational. The 2 things I want to talk about a little bit are parachutes, and then I'll talk about our Super Draco abort system. Our parachutes were really interesting to me as a project because, parachutes have existed for a long time. We went to the moon and came back in the 60s on parachutes. We thought that we knew how they were working until we didn't and started having test failures in mid-2019 and realized that the industry just didn't totally understand how these clusters of parachutes behave. We realized we needed to commit to a redesign to improve the strength margins on them. And normally this would be several years in aerospace industry to go redevelop a parachute system and test it with all these drop tests and things. We said, wow, we really need to fly this vehicle soon. Let's speed run this thing. And so as it had the whole company's backing behind us to go put together a development and test campaign, and in just over 3 months, we're able to redesign, do over 10 drop tests to Delta qualify the system and get into our next phase of testing. So that to me was a really cool example of being able to work with a motivated group of human beings, all with a common goal, doing good engineering. The second thing I wanted to talk about on Dragon was developing the abort system. So this is I'll show a video in a second here, but this is a system of 8 different thrusters that live on the capsule. We like to develop reusable vehicles, so we want to bring the abort system home with us every time. We hope to never use it. And so it lives on the capsule. These thrusters are able to propel the capsule away from the rocket if anything is going wrong. But we did have some things go wrong. I'll show you some of the testing that went right to begin here, though. So we did really a huge amount of testing with both a simulator capsule that you saw in that video with a pad abort test. We set up what we called a module that was 1/4 of the spacecraft. That's what you see on the screen here. And we tested this over and over again and thought that we had a good handle on the system. After we flew our first flight to the ISS in early 2019 with a Dragon 2, we brought it back home over the course of a few weeks, retrofit some things and put it on the test stand to do a full capsule test of the abort system. And at the beginning of that test, blew the entire thing up, which was an unexpected outcome, to say the least. So we had a system that we thought was very well developed, that we understood. We put it on a test stand, blew the thing up, and needed to go through a failure investigation and figure out what we learned. We said, did we step into this test too fast? Did we not understand things? What happened? And it turned out at the end of the day, what we discovered was an oxidation and flammability risk between titanium and the nitrogen tetroxide oxidizer that we use in the system, that at very high flow velocities, you could have particle impact that'll set the whole thing off, and you'll get quite a spectacular explosion. So this was something that we didn't understand. NASA didn't completely understand it. There was one line in an old book from the 1960s about propellant development that we thought that we found maybe some reference to it. But really, like the parachutes, the industry, us, NASA, didn't totally understand what was going on. We had to learn from a failure, work through it, and have a safer system at the end of the day. So we were able to work through understanding and fixes and mitigations on the abort system. And we put this all together into a full-scale vehicle test, which SpaceX is really big on. We like to design and analyze things, but really have not found a better surrogate for just doing an all-up test. So what we did is pulled this all together into an in-flight abort test, where you'll see both of these systems get exercised. We launched a rocket that we knew we were going to destroy and throw away, just to prove to ourselves that the spacecraft could separate at the point of maximum aerodynamic pressure safely. Through this test and data review, and just a few months after that, in May of 2020, we're able to step into our first crew flight test. And this to me on this project is this is the impactful piece. This is work on something meaningful. So it was, you know, as I and the team were working on developing this capsule, we were working side by side with our flight test pilots, Bob and Doug, who had been with us. We knew their families. We knew we had to keep them safe. And watching them say goodbye to their families and go get into our spacecraft, where we had to get them up in orbit and back safely, was like a really profound moment that you know, to be a part of a team that was trusted with that. And we were able to go through our Demo 2 flight successfully, and have basically had a continuous presence on orbit, being the main ferry service back and forth to the ISS for the US since that point over the last 4 years. So to me, this was something. Growing up on the farm, I never expected I would come to MIT. Being at MIT, I never expected I would have a chance to go be the engineering lead to replace the space shuttle and be able to bring humans, you know, human spaceflight back to the US. So really incredible experiences. After we got this program going, I mentioned I've sort of operated on the earlier phase of programs. So we had Dragon moving and operational. I switched over to Starship, and had great hope that I would continue living with my happy little family in LA and would work on this vehicle that's getting built in South Texas, and agreed to work on the program after being asked a few times. None of that held. Within 2 months, I was living in South Texas. We had all moved there, and I had a whole bunch of stuff reporting to me that I asked to not have. But we were there and have made the most of it. So this has been about 3 years I've been working on this program. And I wanted to speak a bit about the point of Starship, the goals of Starship. It is the biggest rocket ever built by a factor of 2. It should be the first, you know, it'll be the cheapest payload to orbit system ever developed when we go operational with it. But the real goal of it is not to be big, but to be the first rapidly reusable, reliable rocket that's been developed. We're flying Falcons very frequently, and the first stage is reusable and quite reliable, but the full system is not. So we've been developing the Starship system, a 2-stage system with the booster. First stage that I'll talk about more, that's my main project, and then the ship, second stage, that has a heat shield tile system on it, much like the space shuttle had. So both of these are designed to be able to re-enter after their ascent mission, return to the launch site, and be flown again, ideally with very little refurbishment. So much more of an aircraft-like model. So that's our goal. You can see that this is all being done on literally a spit of sand right next to the Gulf, down at the very tip of Texas. In the background of the picture is the Rio Grande. So this is as far south as you can get into the tip of Texas. The project that I've mostly been working on in my 3 years down there has been on the first stage, which we call the Super Heavy Booster. The photo here is one of our recent vehicles exiting the high bay building where we build it. And I wanted to share this and pause here to talk about the first part of our problem, which is simply building the machine to build the machine. One cannot just go on the internet and order the 9-meter rocket building machine or call up Home Depot and say, please deliver this shed to build it in. So we have a team of people engineering the vehicle itself. We also have a really significant manufacturing development effort, people designing the machines, doing the automation, designing and building our own buildings and high bays. We have 1 million square feet of factory that's just coming online now that's getting us out of the initial tents that we were building our rocket parts in. So a big portion of the effort is the manufacturing effort, which again ties back to what I was able to learn here at MIT. And we bring in literal coils of steel, turn them into rocket parts, and have a full vehicle come out at the end of it. The next big step after building a thing is testing a thing. Again, I'm going to show you the successful videos here, not the explodey ones, but we've had a number of lessons learned as we press to get into integrated tests on our vehicles, many of which feel like big setbacks, but when you look at the overall rate of learning and the progress of the program, ends up being quite valuable. So this is one of our recent static fire tests of a booster, just giving you an idea of how that operates when we practice starting it up on the launch pad. And this is only 50% thrust, just for reference. So that gives you kind of an idea of the launch pad and the infrastructure and the work that we're doing down there to develop all of that. So tying this all together, we've been working for many years at building starships in South Texas. Just last year on April 20th, we were able to launch our first test flight, which ended in, we called it a success because we got off the launch pad, which was truly a success for us. Priority zeros don't blow up the launch pad. And then worked through a second test flight and a third. I'm going to share a video from our third here where we successfully reached orbital velocity with the ship, which achieved our primary objective of getting to orbit, in short. And our further work at this point is very focused on recovery and reuse, so I'll just share this video quickly.
This is the final go, no go poll for Flight 3 of Starship. Avi 2.
Go.
Stage 1.
Go.
Stage 2.
Go.
Flight director is go for launch. We have liftoff.
Vehicle is pitching downrange. Execute. Vehicle is supersonic. Stage separation.
I love the first stage with 17 million pounds of thrust because it's really fun to work on. But this, I think, may be one of the coolest shots in spaceflight history, which is a vehicle re-entering with plasma, recorded in 4K, sent back live over Starlink internet, which was quite an achievement and very great for what we'll call the scientific value of being able to understand what's going on with the re-entry vehicle. So that was just a highlight reel from our third flight. We're about 2 or 3 weeks away from our fourth flight test here, where we hope to expand the mission either even further than we have already. And then just in kind of closing thoughts here, back to working on something that's impactful and important. The mission really is no joke, get to Mars. And so that's what we're motivated by every day. That's what we're trying to solve for. And the things that get me really excited about that are like developing a system. If you can get to Mars, you can get back to the moon very repeatedly and easily and economically, which seems incredible to me. You can expand what we're doing in LEO with constellations that are actually helping people across the world close the gap on communication and so forth. So it's just, you know, I kind of accidentally stumbled into my career path, I think along the lines of what was shared earlier. I had no grand plan for this. This was just me taking interesting opportunities that were in front of me that led me to MIT and then SpaceX and through these different programs. So, you know, I certainly gained personal inspiration from being able to work on this and hope that it brings that to others as well. But thank you.
So, can you all hear me? Should I step back? Okay. Still can't hear me? There it is. There it is. Unlike the first two speakers, I'm maybe on the other end of the spectrum. I did have a plan from the beginning. The beginning being, I would say, around maybe age 15 or so. Took a middle school course in chemistry and learned about what at that time was called global warming. And I was deeply moved by the problem. I was bothered to my core that there wasn't like an obvious solution to how we would solve it. And my mind did the extrapolation that if we didn't solve it, that human beings wouldn't be able to still live on this planet. And I felt moved enough to my core that I committed myself to want to do something about it. Now, what I was going to do about it wasn't clear. I was only 15. But I did, in my mind, have that I wanted to invent or create the thing or something that would contribute significantly to getting there. And the first slide I have here is actually about the power of teachers and mentors, because recently I was being interviewed and someone asked me, what made you want to be an engineer? And as I was reflecting on that as it relates to the discussion here at hand about career paths, I have found that teachers and the influence that I've had from teachers and mentors, I've had many mentors, several are shown here, but by no means exhaustive. But part of what motivated me to want to be a professor was the impact on students, and that was driven by the impact that some teachers and mentors had on me. And so I'll try to tell two stories, try to make them very brief on this one slide. The first is actually about the teacher that I would say made me want to become an engineer, which unfortunately I don't have his picture. His name was Coach Mead. In high school, he was my calculus teacher. And calculus for me was a turning point. And the reason it was a turning point is because later I realized that all the math and science, well, most of the math, all the math that I learned up to that point, I didn't really know what the purpose of it was. It was like, solve for X, and it's like, why are we solving for X? It didn't really seem all that clear why we need to know geometry and why do we need to know all these things. Calculus was the first time that it kind of all distilled into like, it makes sense, I know what I can do with this. And how that happened was Coach Mead was a phenomenal teacher. He was actually an engineer. And he had this teaching style, which I later wanted to proliferate and somewhat adopt myself, which is that he would take a seemingly absurd amount of time explaining the purpose of what you were about to learn before he actually taught it to you. And this context, this background, this like the why and the what can you do with this was so powerful because it made us have an incredible appetite for the thing we wanted to learn. So I'll tell one quick example. I remember he spent like an entire week talking about this thing we were going to learn next week. And he said that once you learn this thing next week, this is like the key thing you'll need to know to be able to put a man on the moon. And as a high school kid, you're like, oh, whoa, what is that, right? And I also remember he said, once I teach you this, you'll be elite. You'll be amongst the less than 0.1% of the human population that actually knows what this is. And like these things that the way he would cast it, it was just like, oh, what is it? Just tell me already. And so the next week, he taught us what a derivative was. And when I learned the derivative, I'm like, okay. And then I'm like, I don't see how you get to the moon with this. But there was an example problem he did. As soon as he taught us what the derivative was, one of the first example problems he did was he said, suppose you got this company that sells hamburgers. And he had this plot, and he says, okay, you sell the hamburgers for this price, you sell this many hamburgers. If you sell it for more, you sell less hamburgers. So what's the best price you sell it at to make the most amount of money? And I was like, oh, this is interesting. And he solved it with the derivative, and my mind was blown. I was like, you can make money with math? All of a sudden, I got super interested. And it was from that point that I became captivated with this idea of optimization, the idea that there was actually like a best solution and you could prove it. You could prove this is actually the best price to sell your hamburger at. And so that is really what got me interested in engineering and really seeing the path to wanting to be able to invent something, to create something that might do something related to climate change down the line, and connecting that back to ultimately the field of engineering. The second mentor I want to mention here, again, all these are great mentors of mine. There's many more beyond this slide. But I want to talk about Dr. Khosla Abdullah. He was a special mentor of mine when I was an undergrad. He's the one that I would say specifically made me want to be a professor. And there's so many stories I could tell about him. But I actually have a little video here that kind of shows a little bit of his personality, because one of the things that was most critical for me, and it's an interesting point, as we talk about diversity and all this stuff, both my parents were professors. And even with both parents being professors, I still didn't have it on my radar as something I would do. And for me, the idea of being an engineering or science-related professor, I couldn't see myself in that role. All I could think about is, professors with the jacket on and the little patches, and that's not me. I grew up listening to hip hop. I grew up in a certain community. There was a certain way I looked at life. And so I didn't see myself as possibly fitting into that box. And I'll never forget, I went to his office one day. He was a civil engineering professor at FAMU, where I went to undergrad. And I went in his office. He had on sweatpants, sneakers, a t-shirt, and his feet up on the desk, and he was bumping the new Rakim album that came out. And he was sitting there playing with his computer, and for me, that image settled it that, like, I'm him. I know what that's like, but he can do this job doing that. And for then I was like, okay, I can do this job. And this is a little video. He's now the president of Virginia State University. And this is a little video that I guess went a little bit viral a couple of years ago, where a student was going around messing with people playing basketball and trying to make fools of people. And they happened to run up on Khosla. So this is Khosla here. And he smacks it from him. and then he decides to cross the student over. So he for me was someone relatable, that was a professor, that was an academic, but came from the kind of community that I came from and made it accessible and something that I could achieve. All right, I'm gonna move on. This is, I later went on, got an undergraduate degree, FAMU, came to MIT for grad school, master's and PhD, had a great experience. I then I got a job at Georgia Tech as a professor as I was leaving MIT. And then I asked them if I could do a postdoc along the way. And they agreed, and they said, okay, no problem. And I went to Oak Ridge National Labs for a year. Then I called the department chair back again. I said, well, I still got more I want to learn. Can I do another postdoc? He said, yeah, that's okay. And then I went to Northwestern for a year. And one of my great mentors, Gang Chen, who's here, he was my PhD advisor. It's a fateful story. I'll skip the story, but long story short, I ended up with a third postdoc, and I called Georgia Tech back and said, can I do a third postdoc? And the third postdoc was actually at the Department of Energy. And the reason was that I had this kind of engineering background. My PhD was actually on simulating atoms and studying the science of heat transfer. And I wanted to really get back to my core mission of doing something about climate change. And I ended up doing this fellowship at ARPA-E, the Advanced Research Projects Agency for Energy. And that ultimately seeded my ability to kind of get familiar with climate change and the spectrum of problems that we have to deal with on the energy side. By the time I got back to actually starting my position at Georgia Tech, I had a million ideas. I had so many things that I wanted to do and pursue. There was one that kind of rose to the top as like, this is the one. If we do this, it opens the door for lots of new things. And I have worked on that idea for the most part for the better of the last 10 years. And that idea was kind of something I'll say that was something that was seeded in me at MIT and a little bit further nurtured at ARPA-E, which is this idea that we question things. we question if just the way you saw it in the book is the right way, or if you've got a model and the experiment says something a bit different, there might be something in there that we still need to learn. And I used to have a funny phrase that I used to tell my students, which is when the model and the experiment don't line up, Mother Nature is ready to teach us something. And so I started questioning some of the assumptions that we have about what we use to build thermal fluid infrastructure. So I am a product of the legacy that John started with steam engines and all the heat transfer and thermal fluids work. I am a part of that continuum. And over the last 100 years, we've used pretty much just a handful of different types of materials. We use sometimes steel, aluminum, plastics, nickel alloys. Sometimes we might even go so far to like use cement to build pipes and things like that. But there's only really a small handful of materials or types of materials that we can use in order to build a thermal fluid system. And what I ultimately concluded is that there's another class of materials that we really have not explored or tried to make work yet, which are ceramics or brittle materials. And there's a great reason. A brittle material, if you drop it, it shatters, right? And it's nice to not have that happen. But we can actually make systems that survive, that actually function with stresses that are understood and well known. And you can design something with enough of an over margin so that failure doesn't happen. And what this opens up is the idea of using graphite in particular, which is our main material of choice, but also other ceramics and brittle materials, is it opens up a real big window on temperature. Whereas previously, there's probably not many systems you can find on Earth that really operate above about 1,000 degrees Celsius in steady state without active cooling. We now can go to 2,000 C and beyond. And so we're now going to the same kinds of temperatures you see inside of an incandescent light bulb with moving parts and valves and pumps and liquids flowing around at temperatures that are glowing white hot. There's actually a bunch of videos on this I'm gonna skip here. But over the course of 10 years, we've kind of trudged along. As Joe talked about, we just solved problem after problem after problem. And we have moved this forward to a point where we got to a place where it made sense to have a startup company. So where I am now, I'm on leave, moved beyond just a handful of 2 or 3 graduate students working on it to now a team of 16 and more. And everything's getting bigger. The team's bigger. And also the size, the scale of things are bigger. So this block you see here, this is a graphite block, literally weighs a ton. Whereas the blocks we were using to build things were handheld, 20-ish pounds, now it's like a factor of 100 more weight. This box inside my lab, you'll find a 5-foot diameter vacuum chamber that's 10 feet long. For me, that was big when I came to MIT. Now we have a 20-foot by 20-foot by 20-foot cube that we build our things in to keep it in an inert environment. Instead of buying a few pounds of tin shot to pour in order to use our liquid metal, we're now buying pallets of a few tons of tin. And so the scale has gotten bigger. The basic principles are all the same. But there's new interesting issues and problems to resolve, but there's no new science. It's all engineering. We actually understand all the principles involved. So I'll stop there and just wanted to use this as an opportunity to really highlight key pieces on my career path, and especially this notion of teaching and mentoring. All right. Thank you.
Yeah. Good afternoon, everybody. I'm Danny Bronstein. I run the Pappalardo Lab. Woo, I heard? Yeah, great. Did anyone go to 2007 last night? We have a few. Well, how was it? Evan? Yeah. It was good? Okay, good. I'm glad you enjoyed it. Thank you all for speaking. I mean, humbling and amazing work that you guys are doing. One thing that strikes me when you're presenting is you mentioned test, test, test all the time. You're building, Alice, you were doing a lot of consumer feedback in your early days. I just wanted to touch on a few things with the limited time that we have. Let me see here. 2007, last night, I think we witnessed some, I think they're called rapid unscheduled disassemblies.
I've seen those before.
Have you seen
Yeah.
those before? I'd just be curious to know, we learn from our failures. We learn from experimenting. In fact, they're not failures. They're lessons learned. I'm exhausted of all of the lessons from this previous week. I'm wondering if perhaps, Alice, if you start, just if you can reflect on maybe an early discovery and what you learned from that and how you moved your organization forward.
Oh, I mean, in that early testing, thankfully I didn't spend too much time on some of those prototypes because I remember it very vividly. I was at a family's home doing testing on one of those ideas, and the 6-year-old girl could have not looked more bored with what we were doing, and I was literally there to entertain her. So that I think that feedback. I was just picking up the cues from her, but that feedback was like, okay, I need to go back to the drawing board and actually come up with something a little bit more interesting, but maybe bring a few things next time and just try to rapidly get some more information. Also, go and look at what kinds of things she actually is playing with and see what lessons I could draw from that. But yeah, we had plenty of failures that were higher stakes too later. That was an early one.
Okay. Joe? Failures or learning?
Many
Big
failures.
Ones. Yeah.
Yeah, failures are generally a good thing. You don't want to have the facepalm ones where you're like, I should have seen those, but there have been many that I've been through that you do some test and you learn some integrated thing about how everything came together that you just would not have seen ahead of time. So you have those examples of, parachute and NTO things on our rocket that we're working on now. One earlier example from a year and a half ago was basically a detonation that we had underneath the rocket. This is our first vehicle at SpaceX that uses a cryogenic fuel. Cryogenic fuels want to boil off and be gases with oxygen, so that's a difficult environment you've got to manage. So that was an example of a recent one that you learn something that your failure of imagination did not capture previously, and you go redesign for that.
Yeah. We talk about this a lot at MIT. We work with our undergrads, fail early, fail often. I think you even said that, Joe. Do you think, is that unique to MIT, or was that your experience here?
I think the goal is learn early. My lab learnings at MIT were less of a glorious rub than the ones that I've had at SpaceX. But yeah.
And how about Stanford, MIT? We get some perspective there.
Well, I think,
Ooh, you're trying to start something.
No, there's no fighting words. I just want to hear.
MIT. No, I think, especially coming for undergrad, you're used to being able to figure things out pretty easily, right? High school's pretty easy. If you get into MIT, that means high school is probably pretty easy for you. You get here, maybe you fail the first test. Maybe that's what I did. But then you realize, okay, I can't figure this all out by myself. I need to figure out how to ask for help. And I hadn't been used to asking for help before. And that was a big thing that MIT sort of shocked me with, but was helpful.
And how about the hands-on piece that we do here? I'd be interested in your perspective on that. I know, Ashay, from the professor's point of view, what do you see?
Yeah, I think the hands-on piece is unique. I would say the other unique thing is really this, the fearlessness. Sometimes when somebody said to me when I was a grad student here that you don't really know what MIT's done to you until you leave. And I didn't understand that statement until I left. And sometimes it's referred to as like the MIT arrogance. But what I've come to appreciate is that it can be perceived that way externally. But what it really is a level of confidence that gets built into students because there's a fearlessness you have about any subject matter. When you leave here, you don't generally think of any subject as being intellectually intimidating. Whereas in many other schools, there's a culture of it's almost like a way of expressing humility, like, oh, well, that's too complicated. Like, whatever you do, that's too much for me to understand. But here, that's not the culture, right? Like, the culture is actually the opposite. I'm a mechanical engineer. I could talk to someone in bio, and they won't talk to me with some sense of, well, you don't know my field, so it'll be the opposite. It'll be, well, let me just explain it to you because you're here, you can understand it, you can get it, and I think that part is really, really unique. And when I left MIT, I really missed it because there's a sense of if you're here, you can do anything, and that can come off as arrogance when you leave here because you won't be intimidated by anything.
Okay, so outsiders there, if you've hired MIT folks, is it an arrogance? Is there a hubris? Or what Alice, you're looking at me.
I had no confidence coming out of MIT. It took going to another school to realize, oh, actually I do know some things. That was, I think, the best boost for me.
So it was the contrast.
Yeah, it was. Yeah,
that may be the difference between undergrad and grad.
Oh, I see. That's right.
I think maybe even qualifiers and no qualifier. Like
That's
that,
right.
The qualifying exam puts a kind of confidence in you.
Well, you get beaten down.
Yeah,
I think, a little bit.
yeah.
Right. Joe, how was your qualifying experience?
I survived it. Yeah, you definitely get the survivor feeling. You can do anything after that.
Yeah.
Okay. You talked about, Asha, you talked about teams. Clearly the technology, all of your paths has been, certainly fascinating. The power of mentorship is something that's always resonated with me. I'm just wondering, Joe, for instance, your organization's a large organization. I'm just wondering if you can paint a picture for us of, maybe the archetypal SpaceX engineer. What's a culture like, and yeah.
Yeah, sure. I'll try to summarize it effectively. You talked about the hands-on component. The type of person that I've found really thrives at SpaceX is the type that likes to be engaged with both the engineering of their hardware and then the actual build and test of it. Like, we're building physical systems. There's just nothing better than being connected to the actual thing happening. So we've put great effort into co-locating our engineers with where their hardware gets built, so that you're designing before lunch and you can after lunch go work on actually building and testing the thing, right? Just intense co-location. And then the type of person that really thrives in our environment is able to demonstrate real results on a project. They're able to make the first principles decisions that they need to based on physics. They're able to put together a plan and they're able to execute. Those are the things that really make engineers succeed.
So the mens at Manos piece. Yeah. How do you think we can be preparing our students more for those types of environments? Ashe? Yeah.
This answer may not be popular.
That's fine.
I think that, sometimes people refer to it as grit.
Yeah.
I think the idea of being very persevering and not buckling in the face of challenge is something that we look for or try to enhance in students, but we don't actually teach. We don't actually try to actually build that into students as much as filter students who have it. And I think if we can find a way to somewhat operationalize the key traits that make people successful and actually give those things to students, train them to have these things. One of the complaints that might also often come up is, students are evaluated on their ability to communicate, but then we're not teaching communication. And so I think us as faculty kind of taking a position of trying to find ways to actually give students and prepare students for the things that, and give them the traits that will make them really successful. I think those things will enhance our program even further.
Mm-hmm, mm-hmm. And Alice, I know as an investor, you're looking at technology and opportunities. You're also sizing up the people and the teams, right? Can you speak to kind of that balance, or how do you evaluate the people in front of you?
Yeah, we look, one of the first things we look for is, even if it's an early stage team, who have they been able to bring together either on the core founding team or as advisors that are just helping them for free right now? Who have they been able to convince that what they're working on is this really cool solution, even if it hasn't been proven yet, because that's going to be an indicator of how well they're going to hire as the team grows and grows. Another thing we really try to understand, even in the early conversations, is how comfortable are they with getting pushback and feedback, and how adaptable are they? We're not telling them to change their idea or change their approach, but things are going to come up. So how willing are they to adapt?
Is grit a component to this?
Oh yeah, yeah. You have to, what the phrase people use is like, is this founder going to run through walls to make this happen?
Right.
Yeah.
Cool.
If I could add
Yeah.
one thing to that answer, I think there's a key component to grit that has to do with one being really anchored in their purpose in life. I think that's a big area for us to improve. I don't think the majority of our students, and not to pick on our students, the majority of most students or most kids in America don't really know why they're doing what they're doing. They're just kind of meandering and going through the things that are put in front of them. And I think to the extent that we can help students anchor like why it is they're doing what they're doing, what is the real purpose, and why did you choose that? The deeper we can anchor that, the more grit they will have.
Well, Joe, I think you said one of your purposes is to get to Mars as quickly as you can, right?
Speed running Mars.
Speed running Mars.
That's what we're doing.
I'm just trying to speed run Lexington. Okay, so what I'd like to do is before I kind of go to the audience, I'm sure you have some questions. I do want to test a little bit of knowledge here. Okay? It wouldn't be MIT if we didn't do this. So does anyone want to keep
like failing
score?
one of McKinley's exams.
No, volunteers for scorekeeping? All right, all right. All we need, just I don't know what we're doing. Okay, I'm going to list the department number. And you can tell us what this department is. I think, Alice, you probably have a distinct advantage as an undergraduate here, is that right?
I hope so.
Okay. All right. Scorekeeper set? It's kind of lightning round.
Do we just sort of jump in?
We just say
Yeah,
it real
I'm
fast.
going to list a number. Whoever gets it first, just chime in, and the gentleman in the crowd is going to keep score. Course 18.
Math. Come on, guys. We're talking about 18,500.
I mean, I know it's math. I just didn't say it.
Yeah, okay. You didn't. Asha, you work here.
Yeah. I know.
All right. Course 7.
Biology.
Course 3.
Material science.
Materials.
Oh, that was you got, okay, course 24.
Oh, you told us and I forgot already.
I didn't feed you any answer.
Linguistics? Was that what? Philosophy? Anthropology?
No. Linguistics and philosophy. 17.
Poli-sci. Come on.
Oh my gosh. Okay, 8.
Physics.
Physics.
That was
I
good.
got that one.
6.
Computer science.
Now, Joe got that. Yeah, that's right. Thanks, Joe.
I clearly never made it out of building 35.
You know what? I know. If I'm above Papalardo Lab, people say they let you out. 21A.
That one.
Anthropology.
Good. 15.
Management science.
I didn't know we had that. Course 10.
10. Oh, chemical engineering.
Chemical.
Okay, well, look, Alice crushed it. I don't think you guys are going to be able to prevail. Course 2.
Mechanical.
That's it. Okay, thank you very much. All right. So we do have a few minutes. I'd like to just kind of open it up to questions from the audience. We'll have a microphone pass around right here.
Yes, let us know if you have questions, raise your hand and we'll bring the mic to you.
Nice.
Hi, question for Joe. You said that one of the problems was the ignition of titanium with nitrogen tetroxide. So what was the solution?
Oh, we had to let the material scientists in. It was just going back to basics of particle impact and ignition kinetics and showing margin to that for different material combos.
Was the titanium pacified?
No, I mean, it naturally oxidizes slightly, but we basically just go to a test-based program of shooting particles at materials in their respective media and understand the threshold for ignition, and then you use that as an input to design your system around.
Well, you may want to try pacifying it so that the next particles will not do it.
Any questions on passivation?
not on pacification. However, I wanted to ask the panel in general. Yeah, so the question is, which investment, whether it's time, energy, or whatever, do you feel has been the most valuable or like has had the largest return in your lives?
Wow.
I'm not rich, so I don't have money. I have time and energy. And I think so far I am very happy with the time and energy I've spent on the path that I've worked on this particular. I mean, I had to make some early bets of what things to work on, and I'm really happy that I chose what I did. It's paid off. I'm really happy with it.
Alice?
I found that time has gotten harder and harder to prioritize. The further along, the older you get, and when you're just coming out of school, time is honestly, I think your biggest resource to try as many things as possible. I always wish I had more time.
Yeah, I think echoing that, I'll credit Elon for this one, but the only true resource constraint that we have is time. And so that's what we, professionally, that's what we really optimize around, and that often leads to good outcomes like, low cost and getting to your finish line on time and things like that. But it really is, it is true, and the more you have going on in your life, the more scarce that it gets. But the way that I would invest it early on is just taking, I think we kind of mentioned it in some of our talks, but just like immerse yourself in the most challenging opportunity that you have in front of you. Like use every moment you have to challenge yourself, to learn from the people around you. Like that is the best. That's how I've approached my decision making professionally, and that's how I recommend others do it as well.
Hi, Asha. I want to thank you for bringing up some of the mentors you've had in your life. I want to bring up that same question perhaps to Joe and Alice. Were there any very significant mentors you had in your life that led you to where you are now? And how did you find them, I guess, is the big question too.
Mm.
Was it?
It was Alice and Asha.
Things that led us to where we are now?
The mentors, any particular people?
For me, it has been a few. Both of my advisors have been very influential in my life. I won't say too many nice things about Dave because he's sitting right here, but honestly, an incredible advisor that gave me kind of free rein to go investigate the things that I was really interested in and helped me in doing that. And then my advisor at Iowa State, where I did my master's degree, was just similar, a great friend and mentor and helped me. And then the third person is honestly my wife, who has constantly kicked my butt out of my comfort zone and is the reason I came to MIT, because she kicked me out of my comfort zone and the reason I went to SpaceX. So you need to have those people in your life that push you a bit.
Yeah, I think my parents were a huge influence, obviously, but then at MIT, there were some professors that I really leaned on a lot, and when I was going through the classes, one example is 2-6. It was one of the hardest classes I took, but I took it with Professor Brisson, and I just thought he was awesome. And he was the one, when I think I shared this with the group earlier, I got a 52 on the final, which put me at an A in the class. And he's like, you should go to grad school. And I took that advice. So I really appreciated that. But then, yeah, at different stages, different types of people. When I had my toy company, I found this man, Lauren, who had been a toy inventor for 30 years. And he was just so awesome to get feedback on things he'd done, but also just to do ideas and brainstorm with. And yeah, he was fantastic to work with. And then now I work for Khosla, who co-founded Sun Microsystems. He's invested, so he's built really cool companies. He's invested in really cool companies. And he is just constantly getting excited about new approaches and climate and solving the climate problems. So I work pretty closely with him, and he's been a fantastic mentor.
I'm curious, a show of hands, how many people in the audience can remember the name of a teacher or mentor that really influenced you? How about a shout out of names? Anyone remember their names? Woody, of course.
You.
Yeah, right.
Denny.
Thank you, but no. Any others? Gil Strang, of course. Sanjay, yeah, out in the, wow. Okay, so, I think from the educator's perspective, I think we want to make sure, and then in industry too, we want to become, as far as purpose, we want to become the people whose names get shouted out 20 years from now. We want to make a difference, as you guys have clearly done so profoundly. So I think, John, I think we're coming up to the hour. I do want to have one thing, though. Alice, I got to put you up to this.
Oh, mine's over. I conveniently forgot to bring it.
Okay, look, 2008. Does anyone remember? You can.
Okay, I only said I made a yo. I didn't say I was good at yo-yoing. Okay. Oh, this is okay.
So this is a
Okay,
2008 yo-yo. Look, that's technique.
I gotta get Nemo. I gotta get Nemo.
Okay, this is the injection molding project that started it all. All right,
Well,
so. No, nice work.
Clear.
Thank you to everybody, the panel here. John.
Yeah, thank you, everyone. Thank you, Ase, Alice, Joe, Danny, for your remarks, for the great conversation. That concludes the program. However, we do have some food outside. You can follow us out into Hockfield Court, right out the doors, and past the Stata Center, you'll see a big tent, and we have a reception out there to conclude the day. Thanks, everyone, for coming.